Hi everyone, I'm Jeremy Gordon. I'm a PhD student at the UC Berkeley School of Information, and I'm presenting work today titled Covert Embodied Choice, Decision-Making and the Limits of Privacy Under Biometric Surveillance. And to motivate, I want to start with Shoshana Zuboff, who reminds us that sensing devices are already ubiquitous in both public and private life. And what Zuboff terms Big Other includes a constellation of tracking infrastructure that use opaque mechanisms to detect and influence behavior, ultimately to produce revenue and market control. And so our work here focuses on a specific slice of modern surveillance, that which combines physiological sensing and statistical learning methods to make predictions about future behavior of individuals. And we ask, how effective are individuals at evading such systems when they're made explicitly aware of adversarial tracking? So our research questions were, to what extent do signals like gaze and micromotor outputs predict intention? What strategies are used by participants when they're instructed to make unpredictable decisions in a simple tracked setting? And how well do individuals' intuitions about tracking dynamics and how to evade them align with modern technology? So in short, do the strategies that they use actually work? And so we designed a task in which participants play a virtual card matching game based on set, and a virtual adversary tracks physiology and behavior using an eye tracker, skin conductance monitor, and head and controller positions, and attempts to guess which card they'll ultimately choose, either the left or the right. So in each trial, participant is asked to decide which card on the table makes a complete set in their hand, move the selected card into their hand, and do so without their choice being detected during the decision phase prior to selection. And participants completed 44 trials, and in the pre-adversary trials, participants are instructed only to select a card that makes a match. But in the middle of the experiment, the task changes, and participants are informed that they must not only choose the right card, but to make the decision without the computer adversary correctly predicting their choice. And to give a sense of the data that we collected, these are top-down views of controller trajectories on the left, final position in the middle, and final velocity on the right at the termination of the decision phase. And here turquoise indicates trials where the right card was selected and magenta the left. And we can already see here a clear choice correlation in all three of the metrics during pre-adversary trials along the top row, whereas post-adversary data exhibits less stereotyped segmentation, but clear differentiation is still visible in both final position and final velocity. And we can learn a lot more about how participants took on this task by looking at gaze metrics within and across trials. So here the top row shows total fixation duration, with sequential trials moving from top to bottom for 4 selected participants. And here green is the duration of fixations on the chosen card, while blue is for fixations on the other card. And the dotted red line indicates the beginning of adversarial trials. So the bottom row shows the fixated object across the duration of the decision phase from left to right. And these charts show a couple of typical patterns that give a sense of the range of strategies that are employed. So for example, the first column shows a participant who is consistently fixating for longer on their chosen card prior to the task becoming adversarial, but then appears to reverse this pattern by fixating for longer on the opposite card to obfuscate their choice. The second participant reduces fixation durations overall post-adversary, maybe trying to avoid looking at either card, but the duration remains predictive of choice, and a clear pattern emerges in the bottom plot where the last fixation by this participant are highly biased towards the chosen card. And finally, the last participant shows a pattern of fixations pre-adversary that interestingly looks fairly random, but whose behavior changes to prefer fixations on the non-chosen card post-adversary, which of course becomes a predictable signal once the strategy is detected. So we then asked, how well might a machine learning classifier perform on the prediction problem? So given a set of physiological and behavioral data collected during the decision phase, to what extent can a statistical model, in this case we used a decision tree, predict whether a participant will ultimately choose the left card or the right card? So from our 1,200 adversarial trials, we split our participants into training and test groups, such that our predictors were evaluated on trials completed by completely novel participants. And the chart at left shows the change in predictability, with each point a participant in the test set, and points plotted below the diagonal in green, indicating successful reduction in prediction accuracy, and those in red indicating a minority of participants who became more predictable post-adversary. And the histogram at right shows what % of trials could be correctly predicted. And we can see that the largest cluster is on the right, on the upper end of the distribution, showing that most participants were correctly predicted in 75 to 95% of trials. And finally, just to speculate a bit and connect this work to policy, there are many proposals about how to help address the threat of remote sensing in public and private spaces. And I think our findings here indicate that initiatives like surveillance warning symbols from Alphabet and DIY hardware filters may punt the responsibility for privacy to individuals. And so this work suggests that these aren't really solutions, as not all individuals have a nuanced understanding about the dynamics and the capabilities of the algorithms that are operating on their data, nor should they have to. So thank you all for watching.